Hey everyone, and welcome to episode 6 of this logic and set theory series. So, last time we ended off with discussing, or rather, we spent most of the time developing the idea of a theory being a theory sigma being just a set of sentences. And I told you that there were two situations where we might want to have a set of sentences be an object. One are axioms. Axioms are sets of sentences, and that's one thing we want to study. And a second thing that we might want to study is, I forget. We'll get to a legal, a formal definition of this later. But basically, I could even. The whole point of color is I can emphasize things. So everything true in a theory. So the idea is, one set of sentences is axioms, which is like sort of a maximally small set. And another set of sentences that I might consider is the set of everything that's true, right? Everything that a sentence can deduce. And that would be almost like a maximally big set. So, we have these two different angles in which we'll want to be talking about sets of sentences. So we'll go in that order. I'll first talk about axioms. We won't actually really use axioms too much until later. It'll be important that we defined them, but they won't be necessary. But the second thing will be more of what we want to consider moving forward. And just for like where we are, I think I have 2 videos left to talk about propositional logic. And then the very next video, we will be talking about, we'll start developing first order logic. Okay. So without further ado, let's just start talking about axioms, and we'll just define them as is typical. So we will say that delta is a set of axioms for gamma if, and then this is the condition here, so if for every sentence phi is a consequence of the axioms exactly when phi is a consequence of the theory. Okay, so the idea is, and I think this, this might be hard to unpack, and recall this, this consequence notion, the notion of consequence is something we defined last time to mean that that phi is true in every model of the axioms. So importantly, it doesn't matter, and because this is true of every sentence phi, what this basically says is that it doesn't matter if you're in the theory itself or or just thinking about the axioms of the theory. And it also doesn't matter what model of the axioms you've chosen. You always know that if phi is true of the axioms, then phi is true of the theory itself. So in a way, we can try to find, we want, and there's nothing in this definition about this. Like, for instance, it's completely consistent if phi, or if delta is just the theory itself, right? You can always just assume everything in the theory to be an axiom, and then of course that's a set of axioms for the theory. But we want to make this this delta as small as possible. So gamma, we'll just extend this definition a little bit to like a very mathematical notion of smallness. Gamma is finitely axiomatizable if delta is finite. Okay. So that's one notion. It's a very mathematical notion of smallness, right? It's like something small if it's finite, it's big if it's infinite. But I actually think this is a really good notion of the smallness of axioms, simply because for an example, let's say delta happens to be phi and psi. Well, then I'm going to define a delta prime to just be the conjunction of phi and psi. And now I think I'll leave this without proof, but delta prime has exactly the same consequences as delta itself. So what this means is that if I ever have, but this is the key distinction, is that the cardinality of delta is 2, but the cardinality of delta prime is only 1. So without proof, I claim that gamma is finitely axiomatizable if and only if gamma has a single axiom, right? And it doesn't matter if you have, it doesn't matter if you have 20 axioms. You can just take the conjunction, ... You can just take the conjunction of all 20 axioms to reduce it to one axiom, right? So not only is it a good notion of smallness to talk about something being finite, but I can always reduce it to the, obviously you can't have fewer axioms than one. But if I have any finite number of axioms, I can turn it into one axiom by just using the and logical connective, right? I can't do that if it's infinite, though. Remember, all statements are finite. That was the very first, or it was video 2, when we defined the syntax. I said that statements are exactly that which can be produced by a finite application of, rules 1 through 3. So statements are always finite. So if I have an infinite set of axioms, this trick doesn't work. So really, you may be thinking of like, okay, this theory has 5 axioms, but this theory has 4 axioms. But actually, the key difference is this theory has only finite axioms, and this theory has infinite axioms. And of course, just to dispel your wonderings, there do exist non-finitely axiomatizable theories. In fact, ZFC set theory is one of them. So we will see a theory that you cannot get away with finite axioms for. Okay, well that's all for axioms. Like I said, we don't need to talk about that too much. Moving forward, we want to. This will be some motivation, but basically, given sigma, we want some gamma that is every phi true in sigma. That's the next goal, and eventually we will call this a maximal consistent theory. But obviously, I think you know what a maximal theory would be. Like, it's very clear that gamma is a maximal theory, but we're going to need, in order to get to this definition, to first define consistency. So that's the direction we're going in. We want to create a set that represents every statement that's true of, and in fact, sigma here could actually just be a set of axioms, right? So we want to create a set that represents everything true of a set of axioms. That's a very important thing because, we have the set of axioms. Now we want to study the theory, the all the consequences of those axioms, right? Okay, so but like I said, we need to define consistency. So let's start there. But I'll actually begin before anything else with an example. So say sigma, my set of sentences, is phi and not phi for some given sentence phi. It doesn't really matter. Or phi could even be a sentence symbol. So say gamma is phi and not phi. Is this allowed? Like, is this a possible set of sentences? Well, it's almost a trick question because actually, yes, right? This is completely fine. There's nothing to prevent me. And, I can take any set of sentences I want. Like, this is a set of sentences, but there's something, your brain is firing off because there's something wrong with this set of sentences. And obviously, what's wrong is that if phi is true, then this is false. And if this over here is true, then phi itself is false, right? So either way, to some extent, sigma has a false statement. So we need to capture this notion of sigma having a false statement. That's our goal, is we want to only, because thus far, I could have always just taken P and not P as my axioms and been like, whatever, I don't care. So let's try to make a notion that tells us that sigma, doesn't have any false statements in it. And you may be, this is a difficult thing to think about. And this is, it's arguments like this that make me so fascinated with set theory, logic, and model theory as well. Because this is a fundamentally flawed way of looking at things. Right? Sigma is, like I said, when I'm considering a theory, sigma is what's true. So you're wrong to think that sigma assumed a false sentence. Because the sentences that are true, we define truth to be what sigma thinks is true. And there's nothing wrong with sigma thinking that phi is true and sigma thinking that not phi is true. There's nothing like, logically unsound with that. Or rather, to our eyes, living outside of sigma, there is something logically unsound to that. But within sigma's eyes, sigma can pick what it thinks it's true, right? So, you might define consistency to be like, here's an attempted but failed definition. Sigma is consistent if sigma has only true statements. But truth, this is a circular definition. Truth is defined by sigma. So sigma always only has true statements. So we have to attack this from a different angle. And in order to do so, we need to first study a property, a very key. We'll do one proof here. We'll do one proof here of yeah. Anyway, the point is we'll do a proof here that identifies a key property of sigma that we will abuse to define consistency. So yeah, hopefully that makes sense. This is a difficult thing to think about, but these are the sorts of thoughts that we'll have to keep coming back to. Like, remember, in Euclidean geometry, we had the parallel postulate is true in Euclidean geometry and false in hyperbolic geometry. Truth, the truth of a statement is something we've defined. It's something that comes from what we believe, and it isn't something innate. So we have to find a way to get around this to sort of like build this innateness, because it's not something immediately apparent. So this is the proposition I want to prove, which is, I guess I'll do it in red. So sigma proves, so how should I write this? Yeah, so sigma will prove S and not S, or we'll do sigma will prove P and not P if and only if for every phi sigma proves phi. So what this is saying is that if sigma can prove P and not P for some sentence symbol P, then sigma will actually prove any statement. Okay. And what let's before I even prove this, let's back up and talk about the intuition behind all this. What this is saying is that it's actually okay if my sigma thinks phi is true and it thinks not phi is true. But what this actually means is that sigma just thinks everything is true. Sigma thinks every statement is a true statement. That's the only way it can think a contradiction, is if there's literally no false statements, right? And the proof, you can take a second if you want to think about it, I guess. It's not too hard. This could be a fun one to think about, actually. Okay. So, very simply, I claim the... I guess I'll write this out a little more formally, but I claim the following... Or let's write a little bit less. So I'm going to let psi be equal to P and not P implies phi. Or I guess before anything else. Sorry, I'm circling around. Let phi be arbitrary. So now we're going to let psi be P and not P implies phi. And now, what's my observation? Psi is a tautology. Because the value, right, there's a distinction between, like, this is the semantic syntactic. The value of this statement, even though sigma may prove this statement and sigma thinks this statement is true, the value of this statement is false. And thus, it doesn't matter the value of the consequence of this implication, right? If this always evaluates to false, then the entire expression will always evaluate to true. So that regardless of what phi is, this psi that I've built is a tautology. And what that means is I can use that in a formal deduction. So I will write a formal deduction, which is very simple. So I'll switch color so it's more clear I'm doing something different. But the formal deduction will first write down P and not P. And then it will write down the tautology P and not P implies psi. So this is, I'll even give my, this is something from sigma. And this here is a tautology. And so finally, by modus ponens, I conclude that psi is true. So that is, if sigma can deduce a contradiction, then if sigma can deduce a contradiction, it can apply modus ponens to use that contradiction to deduce anything else. And in fact, all that mattered for this proof, and that's we're done, right? This is an if and only if, but this direction is trivial because if sigma can deduce everything, it certainly can deduce this. The key thing, though, is all that mattered was that P and not P had a false value. So I could have plugged in any sentence here that has a false value, and the proof would have gone exactly as follows, right? So this is, and it's sort of the similar thing that we did earlier when we were, this will keep coming up, is there's this semantic understanding of truth, which sort of looks at things from the eyes of sigma. And in the eyes of sigma, in fact, well, this even is syntactic, but we're still proving this. But there's sort of this, we're looking at things from the eye of sigma, but we can always zoom out and use truth tables to look at things a little bit more objectively. And we can always zoom out and use truth tables to look at things objectively. And by zooming out and using truth tables, we can then conclude that what sigma believed was, in some philosophical view, wrong. Okay. So moving on, let's continue the definition. So now we're going to define consistency. And we're going to define consistency. We did that if and only if. And you're tempted to use the fact that it proves a contradiction. But like I said, that doesn't, we can't get anything from that. So we have to use the other end of the if and only if to define consistency. So we say that sigma is inconsistent if, and then here comes that condition we just proved, if for every phi, sigma can prove phi. And then, of course, sigma is consistent otherwise. That was a really bad otherwise. Okay. So we actually define consistency in terms of inconsistency. because it's easier to identify something being, because there's this very clear, the point is that last proof shows that there's this very clear, obvious property that makes something inconsistent. Okay. I want to end today with one more definition. And it's sort of just an extension of this one, so I can write it at the bottom. But sigma is maximal consistent if there does not exist, or whatever. I'll just say if no consistent set gamma is a proper superset. So sigma is a maximal consistent set if it's consistent. I'm continuing off of this. So sigma is maximal consistent if, of course, it's consistent, and if there's no consistent set that contains it. And that's now maximal consistency is the notion that we wanted to build, right? So, if I have any set of axioms, imagine there's some, if you have any set of axioms, imagine that there's some maximal consistent set that contains those axioms, right? And then that set must be everything those axioms think is true. Because if I add any other statement, then it produces a contradiction, right? Okay. So, and that's important. It's actually important we define consistency first, because if we rewind all the way to earlier when we were talking about that, like, one example is I could have just said, if I told you, give me the set that contains, the set of everything these axioms think is true, then I could have given you the set of all statements. And I could have said, the axioms think every statement is true. And as we argued, that would have been internally consistent. Even if the axioms were consistent, there's an inconsistent set that contains the axioms, namely the set of all statements. That's inconsistent, and of course it contains the axioms. So it's important we limit to only considering consistent sets. Obviously inconsistent theories are useless to us because an inconsistent theory always can prove everything. So I've already exhausted all the inconsistent theories. It's only the consistent ones that are now interesting. Okay, so I think that's a really good stopping point. Next time, I guess I'll just give a brief prelude, is next time we will prove that every set of axioms can be extended to a maximal consistent theory. Okay, so that'll be the goal for next time, and that's, it's clear why this would be an important goal, because we want to study the theory of the axioms, so this would be the theory we want to study. Okay, so anyway, thank you guys for watching, and I'll see you next time when we prove the statement.